So we're going to start by doing some examples of some nomenclature here. So first, what we've already discussed, so this will be nomenclatures and examples, and this is our second lecture, so I'll just label these as this. So first, we want to talk about order. So what's the order of a differential equation? Oops. So when we talk about the order of a differential equation, let's get this set up a little bit better so it's square. So when we talk about the order of a differential equation, we're talking about basically the highest derivative there can be. So for example, y prime equals 1, which we solved last time. This is a first order differential equation because there's only the first order differential. Whereas something like y double prime equals 1, remember this was like gravity. This is the second order because there's there's a second derivative involved. Remember, we can write this as something like d to the n of y dx to the n, right? So the order is this n. The higher the n, the higher the order. So first order, second order, third order differential equations. Sometimes we can play tricks to actually reduce the order of the differential equation, but that will come up later. Typically, we want to discuss what's the highest there is. So if there's 1 prime, it's 1. If 2 primes, there's 2. Third derivatives, there's 3, right? So it's the nth order differential equation. So that's the first way to classify it, and usually the higher order, the more difficult things get. The next thing we want to say is linear, or of course the opposite would be nonlinear. What do we mean by a linear differential equation? Well, a linear differential equation, this is easy if you've already had something like matrix theory or linear algebra. But linear differential equations usually have a form something like, let's say, a2 of x, well, let's write it like this, d2y dx plus a 1 of x dy dx plus a 0 of x y equals b of x. All right, this is a linear differential equation, and I've only written it to the second order, but notice that this could go to the nth order. We could easily have a term a n of x dn dx to the n. All right, so this is a linear differential equation, and you probably don't need to know this for this class, but if you are taking something like linear algebra, notice that I can write this as a row vector times a column vector. So for example, this equation would look like a2, a1, a0 times y double prime, y prime, y, right? So this row vector times this column vector equals this thing. This is what's called linear, okay? What do I mean? And let's be careful. Remember that this a2, these are just arbitrary, so a is for arbitrary here. a2 just means the arbitrary function, and I just labeled it 1 and 2 because they can be any function of x that they want to be, right? So these can be functions of x, right, times the derivative. This is linear. What do I mean by nonlinear? So let's say nonlinear. Nonlinear means, right, when I have this matrix like this, I can never have anything that is an order of derivative times itself or another derivative. That sounds fancy, but it's really not that fancy. It just means I can't have terms like y prime times y double prime equals a number, for example, right? This is nonlinear because I have the first order term times the second order term. I can't write this in a linear vector way, so this is a nonlinear equation. Notice also that I can't have terms like y prime squared. This is also nonlinear. So this is what I was trying to say when I say that I can't have any order of derivative times itself, right? This is y prime times itself, or times any other order of derivative. Neither of these is allowed for linear differential equations. And when things are linear, we'll have methods to solve them. When they're nonlinear, it's typically much more difficult to solve them, but we'll talk about some nonlinear equations and some tricks we can use for substitution there. So linear, all these terms are independent of one another. Nonlinear means they can be mixed and matched and to different powers. Okay. The next thing we might want to talk about is homogeneous differential equations. So what does it mean when we say homogeneous? Homogeneous differential equations mean that all terms have the dependent variable. All right, so all terms depend on the dependent variable. So maybe that's a subsection. Hopefully you already know that the dependent and the independent variable. So a dependent variable, if we have a function, let's say y of x, the independent variable is x. X doesn't care about anything. Y cares about x, so y is the dependent variable. Okay? So, for example, all of them, so in homogeneous, we need all terms have to have the dependent variable. Okay? So, all terms have to have the dependent variable. The opposite of that is to say there are terms that don't have the dependent variable. And if there's terms that don't have the dependent variable, right, then they only have the independent variable. What's an example? So what's an example of a homogeneous equation? A homogeneous equation might be something like, well, we already did this one, exponential growth, right? So do all terms have the dependent variable? Yes, this term has the dependent variable y, and this term has the dependent variable y. So all terms have the dependent variable y. Okay? There's other times when we wouldn't have y, right, that this would be an inhomogeneous, right? Just like here we can have nonlinear, we can also have non-homogeneous or inhomogeneous differential equations, right? So for example, this example we did below, it itself would be a homogeneous differential equation as long as this was 0, right? You can't have this extra term that has the independent variable all by itself, right? So you couldn't have this b of x all over by itself. You can't have any x term hang out by itself, right? These are functions of x, but remember if this, for example, was 1 plus x, right? This would be y plus x times y. There's no term there that only has an x and no y or y prime to go along with it. All right, and remember this y counts as the 0th order derivative. All right, so now we have the order, we have whether it's linear or nonlinear, and the very last thing we'll talk about for nomenclature for now at least is well, let's talk about autonomous, as we've already talked about as such an equation. Autonomous. Close enough. So, what's an autonomous equation? An autonomous equation means there's no independent variable. So, no independent. So how can we have something with no independent variables? Remember, if we have y of x or x of t, these are the same. So for example, when we said x double dot of t equals 1, this was our gravity equation. In this equation, t is the independent variable. There's no t anywhere, right? This is just x double dot equals 1. T doesn't appear anywhere inside this. This means this is an autonomous equation. autonomous equations are kind of interesting in that there's no t inside this equation, but solving this equation brings in the t, right? So that's kind of interesting in that case, right? So that's autonomous, and again, we can have non-autonomous equations. For example, if x double dot equaled t, right? This would be something like the acceleration is increasing all the time. This is like if you're in the car and you push down the accelerator harder and harder and harder, the more you speed up, right? So this would be increasing. This is an autonomous equation, okay? So that is the simple nomenclature we have to get started. Those are the 4 things we'll concentrate on. And we'll add some more as we go down. So, but you should know how to deal with order. You should know how to deal or distinguish what order an equation is, if it's linear or nonlinear, if it's homogeneous or inhomogeneous, and if it's autonomous. All right. So for some examples of that, I would like to, at this point you to some online resources that are going to help. All right. So the 2 things I'll point you to is first, open source textbooks. There's this Libre Text, right? So you can just search Libre Text, differential equations. This is the differential equation book for engineers, right? And this is freely available online. This is a nice reference to use, right? And it follows roughly kind of the outline that I'll follow on this video series. We'll skip around a little bit. There's more inside this textbook than we'll actually cover. In a semester, I would say that this is closer to a 2-semester class or maybe a 2-quarter class if you're taking like that. The other thing I'll point you towards, I think, is even better, and that's Paul's online notes. Paul's online notes in differential equations are really excellent. It's outlined very well, and it gives many, many examples, and I really like the way it even does the examples. For example, if we do some basic concepts, right, it gives you examples and it gives you problems, so it kind of forces you to look at the problem and try to work it out, and then it shows you a full worked out solutions if you clicked on it, right? So if you're really interested in understanding it, it's nice because it gives you a problem to do, you do it, and it shows how it's worked out each time. These are really excellent online resources. And again, all the resources that I'll use in this series are going to be free resources, freely available online. All right, so now we'd like to go back to the kind of the second half of this lecture, is to talk a little bit more about, since we have some time, we're going to talk a little bit more about some common equations we come across. Okay, so what are some of those common equations? Let's switch back here to the paper. Okay, and this is the second. Whoops, my pen is running dry. So some common equations. Okay. So we've already talked about several of these equations, but it'll be worth going over them a little bit here to think about. And remember, a part of this video series hopefully is going to get you thinking about how to actually express these equations, express these in words, express these in concepts to really understand what's going on. So perhaps the most straightforward is going to be something like exponential growth. So exponential growth. Let's say we have, you can think of something, for example, like virus spreading or rabbit population. So if I think about the rabbit population tomorrow, or let's say things reproduce every year, just to make it easy. So if I wanted to know the rabbit population, so let's say the population 1 year down the road compared to the population right now. So population 0, population 1. This is one reproduction cycle. So this could be for a virus or anything else. If I ask you, what's the population of rabbits going to be next year? What question comes to mind, or how would you solve this? You should probably say, I don't know, but I could tell you if I knew the reproduction rate and I knew how many rabbits there existed right now. Let's make it simple and say every rabbit produces 2 rabbits, or every couple of rabbits produces 4 rabbits, right? So if the reproduction rate, let's call this R, equals 2, if the reproduction rate equals 2 and you told me the initial population, I could tell you the next population. This would be simple. It's just 2 times the population before. All right? And this is the kind of thing we get when we have exponential growth. Let's think about how to write this as a continuous differential equation. As a continuous differential equation, we want to say the growth or the change in, right? Remember, differentials are a slope, and a slope is the change in. So the change in the rabbit population is equal to or proportional to, so change in, right? So the change in P, right? In words, this just means dP dt. This is the time-dependent change in the rabbit population is proportional to the population, right? And I'll use this sign, this alpha, is used in mathematics to denote proportional to, okay? So the change in the rabbit population is proportional to the population. We might write that as P dot equals, and usually we use K, P, okay? So the change in the population is proportional to the population. And the bigger K is, this is like the reproduction rate, not exactly the reproduction rate in here. This was discrete jumps in population. This is a continuous change in population, right? There is a difference, right? So for example, if you put your money in the bank, it's better to have a continuous change in your interest rate in compounding interest than it is to have discrete. But this is going to be discrete change. This will be a jump. We'll talk more about that later when we talk about population growth. That's a few lectures down the road, few videos down the road. So if we have this, then we already know how to solve this. So I refer you to the previous video. How do I get the change in a function equals the number times a function? Think about that a second. Maybe pause the video. How is that going to work? Well, that's going to work if P equals e to the kt. All right. If P equals e to the kt, right, and we'll call this c e to the kt, what's the derivative? K times c e to the kt, right? Where this is the function itself, right? So the derivative of the function gave you back the function itself. And this is what we wanted. We can even plug this in to our equation. And just to remember, right, remember how we solve this differential equation. We say dP dt equals kp. I can rearrange this to 1 over kp dP dt equals 1, right? I just moved this over to this side. And if these two functions are truly equal, then the integral of the functions has to be equal, right? And so this is 1 over k times the natural log of p equals, in this, and then I put t. Let's move to the next sheet here. And if I solve this equation down here on the bottom of this page, right, I'm going to have the natural log of p equals kt plus a constant. Remember, I got a little sloppy here. Always got to be careful. You want that constant, right? Don't forget that when we take the integral of the derivative, we're always going to lose a piece of information, right? And then I can take e to both sides. And this says the population as a function of time equals, right, this e to the kt plus c equals e to the kt, e to the c, and a number to a constant is just a constant. So this just equals a constant times e to the kt, right? And this is exactly what we guessed before, and this fulfills our equation, So this is the nature of exponential growth. If I was to plot this, for example, this is going to give you some number like this, some function like this, and the larger k is, the more this explodes, right? You want to control this reproduction rate. This is unlimited exponential growth, right? So this happens if you put bacteria in a dish and look at it expand. There's almost always some other limiting factor that's going to happen here in any kind of real system, right? Bacteria uses up the sugar in the bowl or reaches the edge of the bowl. Rabbits eat up all the grass or whatever the case may be, right? So there's almost always some limiting factor that happens as T gets very large. But for small populations in the initial stages of expansion, this is what we have for exponential growth. And this is the standard form you get for exponential growth, right? Notice that K, right, can also be a negative number, right? So we can also get populations that look something like this if K is a negative number, or birth rates are fractions. So I would encourage you on your own to think about what happens, for example, if K equals 1, right? Or, for example, if K equals 10, or if K equals 0.1, or if K equals -1, right? I would plot those out. Those are all interesting cases, and think about what that actually means for rabbits or bacteria or something else if that's the reproduction rate, all right? So this is exponential growth. Another one that's a common one, and this is very close to exponential growth. This would be something like Newton's law of cooling. Newton's law of cooling is, well, unfortunately books or mathematicians like to write it like this, where it's got A's and Y's and T's, but it's easier, I think, if we write it in words, if we say something like T dot, remember T dot, this means a change in, and T, big T is temperature. So the time-dependent change in temperature. So if I was to ask you, if I put something hot in something cold, or something cold in something hot, let's say I put an ice cube in a cup of coffee, what is the change in temperature going to be, right? If the water is cold, right, it's not going to change that fast. If the water is boiling, it's going to change even faster. So the time-dependent rate of change is going to depend on the difference in temperature. So for example, we'll have B, let's say B just is the body of water minus the temperature, right? This is the difference in temperature. So this would be the difference in temperature between the water and the ice cube, right? And then we also need something like the specific heat. Like this is how fast temperatures change, how easy it is to change the temperature of different subjects. So if we have these kinds of things, then this is basically how cooling takes place. And what happens if T, the temperature of the object, equals the temperature of the bath? Well, then the difference in temperature is 0, and then the change in temperature is 0, which makes sense. Once the ice is the same temperature as the water, or the thing you put in the water is the same temperature of the water, then the change in the temperature doesn't change anymore. So this is going to result, so if this is the temperature of the water and you put something hot in it, it's going to go down and gradually reach that steady state temperature. If you put something cold in it, it's going to come and gradually reach that steady state temperature, right? So everything is going to tend towards the temperature of that bath, okay? So this is Newton's law of cooling. And again, you get these kinds of, and we'll solve this directly in coming videos. But you get this kind of asymptotic behavior in time. So we have a little bit more time. Let's talk about one more interesting function that we'll spend quite a bit of time on about 3 or 4 lectures down the road. And that's oscillations. So So oscillations, sometimes called mechanical vibrations, basically things that bounce back and forth and repeat themselves. So what's an easy, well, ones you probably know are a pendulum, like a grandfather's clock. It swings back and forth and back and forth, or something on a spring, right? So let's say we have a surface, we have a spring, we have a mass attached to that spring, and here I drew it horizontally, but you could draw it vertically if you wanted. What happens if I stretch that spring? If I stretch it and let it go, it's going to go back and forth and back and forth and back and forth, right? So if I looked at that position of that spring, I stretch it out, and the position of the spring is going to go back and forth and back and forth, something like this. I drew it kind of poorly, but you get the idea, right? So we have kind of an idea physically, and the same thing's going to happen for the pendulum. We have an idea physically of what's going to happen here. The physics that governs this, the equation that governs this, is Hooke's law. Hooke's law says F equals minus kx. Okay, what does this mean? This means the force on the object is proportional to how far you stretch the spring. If you stretch the spring twice as far, the force is twice as much. So this is our differential equation, and remember from before, F just equals mx double dot, all right? Where force is mass times acceleration, and acceleration is just the second derivative of position. When you have something like this, a spring, it oscillates, right? And I can tell you how it oscillates. For example, it always takes this time it takes to oscillate is called the period, and this period is 2 pi times the square root of k over m. You might have learned this in a physics class or looked at oscillations and thought about this time. And it's one of those things you have to memorize. Hopefully, after this class, you won't have to memorize it. You can just determine what it should be. How do we actually get to that equation? Well, if we look at this differential equation, we have x double dot equals minus k over m times x. And I'd like you to think about what function x of t satisfies this equation. All right, so you might want to even pause the video a second and think about what satisfies this equation. All right, so what kind of numbers might you say? Well, you might have looked back at our exponential growth and said, well, that worked pretty well there. There we had the derivative of a function equals the function itself, and that was exponential because we get the function back. Well, here, this should be something very much the same way. We're not just taking the derivative, we're taking the derivative of the derivative, but we get the function back when we take the derivative of the derivative. So why can't we have something like e to the, and I'll just call it alpha x. Well, if we have e to the alpha x, what do we get for a derivative? Alpha e to the alpha x. What do we get for the second derivative? Alpha squared e to the alpha x. Well, that's close. This is just a number, so we can make it equal to k over m. But how do we get that minus sign? That's tricky to get that minus sign. Let's say instead we said e to the minus alpha x. Oh, that's looking better. So now we take the derivative and we get minus alpha e to the minus alpha x. And we take the derivative again and we get minus alpha times minus alpha, which is plus alpha squared e to the minus alpha x. So yes, we got the function back, but we never got our minus sign back, even though it's plus or minus. So we need to take the second derivative and get the minus sign. Neither one of these, right, neither one, this or this, those did not work for us. How can we get a minus sign? Well, we can get a minus sign by taking imaginary numbers. E to the I alpha x. What's the derivative? I alpha e to the I alpha x. What's the second derivative? I times I by definition equals minus 1. So this is minus alpha squared e to the I alpha x. And this is the original function. So we got our minus sign, all right? So when we take second derivatives and we get minus signs, be on the lookout for for higher order derivatives, often we have to play tricks with imaginary numbers to get the minus signs we want. Notice that e to the I alpha x can also be written as sines and cosines, which makes sense because if I have the sine of alpha x, what's the derivative? Cosine of alpha x, well with an alpha here, what's the derivative of the cosine? Minus alpha squared sine of alpha x. And if I have cosine of alpha x, the derivative is alpha sine alpha x with a minus, and the second derivative is minus alpha squared cosine of alpha x. So either the plus or minus I alpha x works, cosine of alpha x works, sine of alpha x works. All these are possibilities that we can use. All right? We'll talk about how to distinguish these. You can imagine that a lot of this is going to be with using initial conditions, right? And this is the simplest. This is called an ideal harmonic oscillator because there can be things like drag and driving forces that make it more complicated. But when we have mechanical oscillations due to Hooke's law, so we'll go 2, 5, right? We can solve with these sines and cosines, okay? So, for example, if we want this to work, and a solution might be, if we pulled it out to start, then we'd say x of t equals, well, we would say x naught times cosine of k over m square root of t. All right? I'm not saying that this is the only solution. We'll talk about how to get the solution, but let's just check if this is a solution. It's one possible solution. And how do we do that? We plug it back into the equation and see if it works. So, what's the derivative of this guy? It's k over m x naught sine of k over m t. Right, and the derivative of the cosine is minus, and this is a square root. What's the derivative of this? It's k over m again, right? So this is k over m x naught cosine of k over m t, right? And this whole thing just equals x of t. So we have the second derivative of x of t equals k over m with a minus sign times x of t, and that's exactly what we wanted. So this definitely checks out, and we get what we want in this situation. So these are mechanical oscillations, and we'll talk about that a little bit more. All right. There are other equations that we aren't going to go into as we're running short on time, but notice that these come up in all kinds of physical equations, right? So there's population growth, anything with forces on it has these equations, and anything that oscillates also have these equations, right? So for example, the wave equation. Wave equations are kind of interesting because there we have the change. So let's say this is our wave, is something like psi. We have the change, the time-dependent change in the wave can be equal to or proportional to the spatially dependent change in the wave. Okay? This is the generalized, let's say, wave equation. And this is just comes up in Schrodinger. Comes up in all kinds or any kind of propagating wave. All right? We want to look at one other thing here quickly. And we can see, for example, if we're, I'm giving physical examples just because it's easier to picture. But of course, these kinds of equations also dominate when we talk about electromagnetic equations. And circuits also obey these equations as differential equations, and we'll get into more examples there. For example, Maxwell's equations in differential or integral form can also be written like this. And notice that this triangle, this triangle here is the del operator. this just means this differential. And this means differential, and this means differential. So you can see that space and time are coupled together with differential equations, and electric and magnetic fields are coupled together with differential equations. So these are all over the place in physics and mathematics and engineering. So that'll be the last of the lecture for today. Next time we'll continue on and actually start the real work of figuring out differential equations. We'll look at solving simple first-order differential equations by taking antiderivatives, which are integrals, and by looking at slope fields to give us a way to kind of track down or get an idea of what some equations and some solutions should look like. So that's what we'll do next time. Thank you very much.